Greetings to all, and a warm welcome to the lecture series describing chemical bonding and intermolecular forces. I hope you remember from the previous lecture that a bond between two atoms with different electronegativities is polar, and a diatomic molecule containing a polar bond is a polar molecule. Electrons in a polar covalent bond spend more time around the more electronegative element. This can be represented either by a vector showing the direction of the molecule's dipole moment or by delta plus and delta minus symbols indicating the distribution of bonding electrons. Interestingly, whether a molecule with three or more atoms is polar depends not only on the polarity of individual bonds, but also on the molecule's geometry. For instance, both the molecules of carbon dioxide and water contain two identical atoms bonded to a central atom and two polar bonds. However, only one of these molecules is polar. To understand why, think of each individual bond dipole as a vector. The overall dipole moment of the molecule is determined by vector addition of the individual bond dipoles. So, in the case of carbon dioxide, we have two identical vectors pointing in opposite directions. When these vectors are placed on a Cartesian coordinate system, they have no y component, and their x components are equal in magnitude, but opposite in sign. Thus, the sum of these two vectors is 0 in both the x and y directions. In other words, although the bonds in carbon dioxide are polar, the molecule is nonpolar. The vectors representing the bond dipoles in water, although equal in magnitude and opposite in the x direction, are not opposite in the y direction. Therefore, although their x components sum to 0, their y components do not. This means that there is a net resultant dipole, and the molecule of water is polar. At this point, it may be useful to review your knowledge of vector addition. You might recall from high school that there are two main methods for adding vectors. In the triangle method, we add vectors by placing the tail of one vector at the head of the other. The resultant vector is then found by joining the tail of the first vector, labeled here as A, to the head of the second vector, labeled as B. In the parallelogram method, the two vectors are joined at their tails, and parallel lines are drawn to create a parallelogram. The diagonal of this parallelogram represents the sum of the two vectors. Now, let's see how the dipole moments can be used to distinguish between molecules that have the same chemical formula but different arrangements of atoms. Such compounds are called structural isomers. For example, there are two structural isomers of dichloroethylene, both presented here. Since the individual bond dipoles sum to 0 in trans-dichloroethylene, the trans isomer is nonpolar. In strong contrast, the bond dipoles in the cis isomer do not cancel one another. Therefore, cis-dichloroethylene is polar. Because of the difference in polarity, these two isomers can easily be distinguished experimentally by measuring the dipole moment. The final figure in this lecture shows examples of polar and nonpolar molecules, all with polar bonds. Keep in mind that, in general, molecules in which the central atom is symmetrically surrounded by identical atoms are nonpolar. In other words, for molecules with identical terminal atoms, certain symmetrical shapes, such as linear, trigonal planar, tetrahedral, square planar, trigonal bipyramidal, and octahedral, result in nonpolar molecules even if the individual bonds are polar. Examples of such molecules include boron trifluoride and tetrachloromethane. The situation changes significantly when at least one of the terminal atoms is different. For instance, compare tetrachloromethane and chloroform. In tetrachloromethane, the central atom is symmetrically surrounded by identical atoms, causing the dipole moments of individual bonds to cancel out, resulting in a nonpolar molecule. However, in chloroform, one of the chlorine atoms is replaced by hydrogen. This disrupts the symmetry, so the bond dipoles do not cancel out, making chloroform a polar molecule. To sum it up, in this lecture, I described the relationship between molecular geometry and polarity. You already know that the dipole moment is a measure of the charge separation in a molecule containing atoms of different electronegativities, and the dipole moment of a molecule is the sum of whatever bond moments are present in the molecule. In the next lecture, you'll be introduced to intermolecular forces and learn how a molecule's polarity influences the strength of these forces. Thank you for your attention.